Hi Year 9, welcome to this video going over the graph questions that I set. So the aim of this video is for you guys to review your performance during these worksheets. So to do that, what I have put together is a worksheet that goes along with this for you guys to complete. So let's have a look at that worksheet before we go through the work. So I just can explain what I want you to do on it. Okay, so here is our worksheet. So what I want you to do is you can either print this off or fill it out on screen. Both will work. But you can see you're going to use the mark scheme provided. So I'm going to email out as well the mark schemes that go with this work to assess your work. So as I'm going through it, you can either follow what I'm doing to get your marks or use the mark scheme. Both are acceptable. For each question, write your score below. So below is on the second page. So when you do a part of a question, I want you to write your score in here. So for example, if you're doing this question, 1i, what you will do is whatever score you get out of 2, you're going to put in there. Now in the comments box, what I expect you to do is to go through and be honest with yourself. Did you get the marks? Didn't you get the marks? Try and work out why you didn't get the marks. Was it you didn't understand? Was it that you misread the question? Was it a term that you weren't sure about? When it comes to graph, was it poor use of a pencil or whatever? Once you've done that for all the questions, you can put your total score in this space here. And then I'd like you to effectively do 2 stars and a wish. So 2 things you did well during this worksheet and 1 thing that you would improve upon if you had a chance to do it again. When you've done that, you can email through this sheet to your teacher for them to have a look and see how you got on. Alright, so let's have a look at the work then. Okay, so question 1, let's make me a little bit smaller. Alright, so the circuit here is used to investigate how the current changes for different lengths of a wire. Each wire has the same thickness and is made from the same material. We have the results from the experiment as displayed. Okay, so we have our results. The student carrying out the investigation cannot say if these results are repeatable. Explain is our command word. What she should do to enable her to judge the repeatability of her data. So, repeatable data means that every time you do the experiment, you get the same value. We've only done the experiment once here, so we don't know that. So the first thing we need to do is to say, repeat the experiment. 2 marks, we need a second point though. So what will our second point be? Well, we need to then judge the repeatability. We need to make some comment about how we would know it. Well, it's repeatable. So then judge or compare, are these the same results as the first go or first try? Okay, so repeat the experiment, then judge, are these results the same as the first go? That's how we would know whether we had repeatability or not. The student correctly suggests that the resistance of the wire is directly proportional to its length. So if you look, the words correctly and resistance are in bold. And then we've also got directly proportional is important and length is in bold. Explain again how the results in the table agree with this statement. So we're going to have to make some reference to this table. Now, if we look back at our formula page or from work that we've done previously whilst we're in lockdown, we did a bit on resistance and we found that resistance is voltage divided by current, to help if I rearrange this. So resistance is voltage divided by current. So what does this mean for us? Well, this means for us that if resistance of the wire is directly proportional to its length, this means that resistance of the wire equals something times by the length of the wire, or proportional to. So this is what we're looking. If you've watched the video on graphs, talk a little bit about this in the video on graphs. So how can we have a look at this from our data? Well, we could do a few things. We could look at this set of data, and we could look and work out resistances going through. It's 3 marks, 1 mark for working them out. That's perfectly acceptable. We could do it just by looking at the numbers. So because voltage stays the same, we can have a look that resistance is inversely proportional to current. So as resistance goes up, current would go down. And it would mean that if we did this times 2, then our current would go to a half. Okay, now if something's directly proportional, it means that whatever we multiply one side by the other side. So if we look at this, if we double the length, our current halves. If we do that again, where's our other ones? 30 to 60. Our current halves. Tripling makes it go down by a factor of 3. So that's times 3. That's times a third. So we can do it without actually doing any maths or any proper maths here. So we can say that if we double the length, the current halves. So that's going to get us 1 mark so far. As voltage is constant, that gets us our 2nd mark. The resistance is doubling. Now that is quite a tricky answer. I wouldn't expect everybody to be able to do it that way. The more likely way I think people will do it is by doing this, by going, right, well, resistance is voltage divided by current. And then do like a column here for resistance. Let's do a column for resistance. So that for each of these we can put the resistance in and we can compare them. So that's going to be 2 ohms. This one is going to be 4 ohms, 6 ohms. Then we're going to have 10 ohms. Then we're going to have 12 ohms. And then finally we are going to have, that's the only I can't do it in my head, so I would do 1.8 divided by 0.12, 15 ohms. And then that way we can make the same conclusion, that if we double this, we double this. Therefore it's directly proportional. Okay. Plot the data on the grid below and draw a suitable line. Okay, so they've already drawn the scales in. So if a graph, generally when it comes to graphs in the WJEC, if they're 3 marks, your 3 marks are going to be 2 for the points, 1 for the line of best fit. If it's 4 marks, then there'll be 1 for the axes as well. And that is pretty much always what the marks are worth. So we're going to plot the data. Now annoyingly, I printed this out, double-sided save paper, which means that the data that I need is on the opposite side. So I'll have to flip over. Okay, so we're going to plot this data. I'm going to go, might as well do that quickly. You don't need me to do this in normal speed. So here we go. Okay, so there's our graph. Now, a couple of things with this graph to bear in mind. There is no point at 40 centimetres. There is no point at 70. There is one at 50, 60 and 75. WJEC, they seem to like this with these graphs, like missing out points, so that they actually are, or you are, as the student, having to properly plot the data. Now, if you look at this, that is quite obviously a curve. It is not a straight line of best fit. So we go with a curve. And remember when I said about graphs, we like to go like this with our hand. So we like to go with a nice sweep, like so. A few practice goes, and then we go for it. Now, if I handed this in, I am going to lose that line of best fit mark because I'm too far away down here. This doesn't curve round far enough. So let's get a rubber and let's rub this out. Now, hopefully one thing you've noticed is I've rubbed the whole line out. I've not just rubbed out the bit that I got wrong, I've rubbed the whole thing out. And I've tried to rub it out totally so there's none left. Reason why, if you've got wispy, jointed, double lines, you're not going to get the marks. You might as well rub it all out. Start again. Okay, so something like that. So, marking points here. 4 marking points. In terms of the lines, in terms of you get 2 points, 2 marks, getting all your points within one small box. Yeah, so one small box around that. Yep, that gets the mark. That gets the mark. That gets the mark. Yeah, yeah. So those would be okay. Alright, so I would get 2 for my points. Line of best fit. So, line of best fit has also got to be within one small square. So I just about get it there. And the rest, yeah, yeah. So I would get that. So I would get my 3 marks there for my graph. So when you're marking this, those things to take care. Make sure you are within one small square with your points. Your line is a single line. It's not too wobbly. And it is also within one small square. Alright. Describe the relationship between the length of the wire and the current. So again, if you go back, watch the graph video. Graph video, we go through all these different shapes. Alright, so this is, you could say, we've got a few different things here. As the length of wire increases, current decreases. You could you want somewhere talking about the rate. The best way here is, as I've already said, that sort of shape of graph, we talk about inversely proportional. So length, or current, sorry, inversely proportional to seem to be having some problems with my camera here today. Current inversely proportional to length. Seems to be a little bit iffy, but not to worry. You can see that there. So describe the relationship between the length of the wire and the current. Current inversely proportional to length. And the 2 marks there, basically writing the word inversely gets you those 2 marks. The wire used in the experiment has been labelled by the science technician as 0.2 ohms per centimetre. Use your graph and the equation V equals IR. Explain if your results for a 45 centimetre length of wire agree with the information on the label. So, if it's 0.2 ohms per centimetre, in 45 centimetres, what resistance would we have? Well, what we're going to do is 0.2 times 45, which is 9. So we would expect that 45 centimetres would give us 9 ohms. So we go to our graph. 45 centimeters. 41, 2, 3, 4, 5. And that gives us a current of 0.2 amps. So from our graph, 45 centimeters gives us 0.2 amps. R is V divided by I. So 1.8 volts divided by 0.2 amps gives us 1.8 divided by 0.2 gives us 9 ohms. Therefore, correct. Now in terms of the marks here then, so it's 4 marks and what the 4 marks are given for. So the 4 marks are given for 1, using your graph, reading off whatever your current value is. Second mark is for realizing that 45 centimeters should be 9 ohms. Third mark is for doing this equation here. And then the final mark is for saying yes or no based on your data. Now, what you might find is that if you draw your graph wrong, you don't get 0.2 and you might get a different answer. It's based on your graph. It says use your graph. So that's fine. Because here it says use your graph, it's based on your results. Okay, so that's question 1. On to question 2. Now, question 2 is partway through, starts with part D, because the first part of this question was all about transformers, which you haven't done yet. I just wanted the graph drawing bit. Now, some people might say, well, that's unfair, but none of this question actually asks you to explain anything other than do the graph. Even this complete the table, you should be able to do this question by looking at the pattern in the table. So if you look, if I double the number of secondary turns, I double my output voltage. If I have 4 times the turns, I have 4 times the voltage. So what am I going to have here? I've doubled the voltage, I need double the turns. So the missing number is 100. Plot a graph of the output voltage against the number of turns. Again, 3 marks. So 2 for the point, 1 for the line. Okay, so again, do this quickly. So this time, clearly a straight line. And there's my graph. Again, points exactly the same as before. So you get 2 marks if all your points are within 1 small square. And third mark is for the line going through all the points. Describe the relationship between the output voltage and the number of secondary turns. So we look at our graph. Straight line through 0, 0. Immediately, that's directly proportional. Straight line through 0, 0. Directly proportional. So output voltage is directly proportional to number of secondary turns. Let me just... Okay, hopefully that's a bit better now. Use the graph to find the number of secondary turns required to give an output voltage of 5 volts. So it says use the graph. That probably means they want to see some evidence of you using the graph. So I want 5 volts. Halfway between 100 and 150. So the number you're looking for here is exactly 125. Because this is a straight line graph, there's no tolerance. It has to be exactly 125. Oh, by the way, in this question, 2 marks. Basically, you say directly proportional, 2 marks. Job done. Okay, question 3. If you look at the mark scheme, there's a part 5 which I've taken out. That's not there. So don't worry about part 5. Took that out because you would need to know something about transformers, which we've not done yet. Alright, question 3 then. Complete the table. So you've got some information with something important here. 4 lengths. Lengths is underlined, so that must be important. Complete the table showing the missing mean time at 3 centimeters. So mean time, add them up, divide by how many there are, and that's 1.3 in this case. See, my camera's still no better, but 1.3. Plot the data on the grid below and draw a suitable line to show how the wave speed depends on the depth of water. 3 marks. Okay, so this one's only worth 3 marks, but they are going to expect you to do your axes. So it's going to be axes 1 mark, points 1 mark, line 1 mark. That's what they're going for. Now, when it comes for the axes, that piece of graph paper has been specifically drawn that size. It could be wider, it could be taller. So it means that the numbers are going to fit perfectly. Okay, so we're going from 0 to 3 on depth of water. So we've got 1, 2, 3, 4, 5, 6. So we could go halves. So 0, 0.5, 1, 1.5, 2, 2.5, 3. So that gives us our depth of water axes. Always worthwhile just putting the little tick marks in. And we want our wave speed. Wave speed. Ooh, come on. Hopefully that might make our camera a little bit better. So we're going up to 69. And what have we got? 1, 2, 3, 4, 5, 6, 7. So we'll go up to 70. So we're going up to 70. Up to 70 up here. Again, I'm going to plot this graph. I'm going to have to do a lot of tossing and turning because I've printed it off enough anyway. In real exam papers, they will make sure that they're either like this, side by side, or one above the other, not like I've printed this. So, 0, 0. Right, there's the points plotted. Like I said, careful, said before, they like missing 1 out. Here they've missed 2.5 out. So when you come to do it, take care that it goes, you've missed 2.5 out. Don't put the 3 on 2.5. Right, our line, again, quite clearly a curve. So I'm going to turn my paper like this. I want to go from 0, 0. So let's practice. Go for it. Ooh. Didn't practice enough. There we go. Perhaps a little bit wobbly. I think I'd give that the mark though. That's quite a horrible line to draw. So the marks, like I said, 1 for the axes. Yes, get the axes marked. 1 for the points. I get my points. And 1 for my line. Go on. I'm going to give the line with the benefit of the doubt. They're going to be kind. 1 for the line. That's a horrible line to draw. So yeah, there's our graph. Okay, part 2 then. Describe how the wave speed changes with increase in depth of water. 2 marks. Okay, so we want to describe how it changes. So, first things first. Whenever we do these and it's 2 marks, if it's not a straight line, marks are always going to be 1 for how it generally changes, 1 for the gradient. So as depth increases, speed increases. 1 mark. At A, we now need to talk about the rate. So the rate is the gradient, how steep this line is, and it's probably easier sometimes, you know, practice this, I can spot it straight away, but get your ruler, put it on as a gradient, look, and follow it along. What's happening to our ruler? Is it getting steeper or less steep? This case, less steep. So therefore, it's at a decreasing rate. Use the graph to find the wave speed at 2.5 centimeters. So wave speed at 2.5 centimeters. Draw it on your graph. Make sure the examiner can show that, see that you've used your graph. So for me, that's 65. They allow anything, so they are allowing 64 through to 66 because it's a curve. Use data from the table and an equation on page 2. Now I didn't give you page 2, but at the end of the day, you're doing this at home. You've got resources. You could go and try and have a look at what equations you're given, or you could have emailed. You could have asked, said, "Sir, I've got page 2. What's the equation?" The equation we're looking for, though, is that speed equals distance over time, and we want the length of the plastic tray. So we want distance is speed times time. So we want to calculate the length of our plastic tray. Which speed are we going to use? Well, it doesn't matter as long as we use a correct pair of data, as long as we use any of the correct data, it's fine. So why not? Let's go for one. Let's go for this one. This one makes a lot more sense. 3 and 30, nice round numbers. So we're going to have 30 for the speed times by 3 is 90 centimeters. So is our tray 90 centimeters long? Well, this is where I said about this bit being important. 4 lengths. 90 centimeters is 4 lengths. So 90 centimeters equals 4 lengths. So 1 length is 90 divided by 4, which is 22.5. Now they allow a range. If you don't use 30 and 3, you might get a little bit either side. You might get anywhere from 22.4 to 22.6. Pardon me. Alright, moving on. Question 4, is it? Yeah, question 4. Now, my printer chewed the top of the page up, but that's okay, you can still read it. Okay, so the first bit is a bit of revision on circuits, or done stuff on circuits, bit of revision of that. Underline the word or phrase which correctly completes the sentence. Current through resistor R is measured using an ammeter. Ammeters are always connected in series, so it's ammeter for 1 mark, series for 1 mark. The current through the resistor is less than, the same as, or more than the current through X. Well, these two things are in series with each other. So the current has got to come along, go through this and through this. Can't go anywhere else. So same as. X is a variable resistor. Resistor with a line through it, variable resistor. Following measurements were taken. Plot a graph, draw a suitable line. 3 marks, 2 for the point, 1 for the line. Again, managed to do myself here, so do this in fast forward. Okay, 0 and 0, 0 and 0, 2 and 1. So there we go, there's our graph. Likewise, done it again, they've missed out 10. So take care of that you go all the way to the top corner. Use an equation, use the graph and the equation resistance is voltage divided by current to calculate R. So they want to see you're using the graph. So let's just draw these lines on of us pretending to use our graph, 6 and 12. So it's going to be resistance is 12 divided by 6, which is 2 ohms. They want to see you've used your graph though for that. Okay, again, this question has another bit at the beginning, and I've missed that out. On to our last question. Just want the graph bit. So, plot the points, draw a suitable line. 3 marks, 2 for the point, 1 for the line. Okay, so a couple of things here. One, it goes 40, 60, 80, then 90, and 90's halfway in between those two, and then 110. So take care, there's horrible scale on, or horrible readings on the bottom one. This is a curve, so let's draw our curve now. We don't know anything about the data below 40, so we can only draw for the points we've got. That point doesn't look right. 93. Right. Okay. The 90 point is an anomaly here. Because if you look, doesn't matter how you try and plot these. Now, in fact, they will allow you in this graph to draw a straight line, but I suppose could be a straight line like so. Okay, so in terms of the points, 2 marks, get your points right. 3rd mark for your line of best fit. To me, that is an anomaly. It doesn't fit the pattern of the rest. You can see the rest make a nice curve. That one doesn't fit that curve. So I've gone with that. Right, anyway, on to things. Describe the relationship. 2 marks. So same 2 marks. Does it increase or decrease? So rotor diameter, or as rotor diameter increases, power increases. 1st mark. The 2nd mark, gradient at an increasing rate. As this goes up, this graph is getting steeper and steeper. Final one, use an equation from page 2, calculate the efficiency. The useful power is 5 megawatts, the output power is, useful is 3, output power is 5. Well, efficiency is useful over total, so 3 divided by 5. You can worry about the megawatts, which is times 10 to the 6, but they cancel, so it doesn't matter. Times by 100 to make it a percentage. So 3 divided by 5 times by 100, 60%. Okay, so apart from this graph, that was hard. That's a hard graph. Hopefully, then. Okay, so hopefully year 9 then that helped out. Going through some of that stuff, seeing how errors and things like that can creep in. Like I said, common mistakes people will make on that will be drawing straight lines when they should be curves, not getting those points within one small square, and they are sticklers for that. That is our accuracy. Whoops. Yeah, really close look, me tidying up. And once you've done that, please use that sheet, reflect on your performance. Hopefully, might see some of you next week. Thanks for watching. please go and look at the other videos on this channel. Also put one up this week on fossil fuel power stations, which is going to be a topic you might do a little bit of work on over the summer. Like I said, guys, thanks for watching. Subscribe to YouTube, follow us on Twitter for our regular updates.